So hello everyone and welcome back to Neetopedia, that is Neetka Encyclopedia, and we are back with the physics audiobooks of electric charges and fields. In the previous audiobook, that is part 1 of this chapter, we had already completed till 1.9, and today we'll be starting with electric flux. Please note that all the chapters of modern physics, EMI, AC till semiconductors has been finished on our channel, and you can check it out in the physics audiobook playlist, or just click on that top I button of the video and you'll get the link to it. So without wasting our time, let's begin. 1.10 Electric flux. Consider flow of a liquid with velocity v through a small flat surface ds in a direction normal to the surface. The rate of flow of liquid is given by the volume crossing the area per unit time vds and represents the flux of liquid flowing across the plane. If the normal of the surface is not parallel to the direction of the flow of liquid, that is to V, but makes an angle theta with it, the projected area in a plane is perpendicular to V is delta ds cos theta. Therefore, flux going out of the surface ds is V dot n ds. For the case of electric field, we define an analogous quantity and call it electric flux. We should, however, note that there is no flow of a physically observable quantity, unlike the case of liquid flow. In the picture of electric field lines described above, we saw that the number of field lines crossing a unit area placed normal to the field at a point is a measure of the strength of electric field at that part. This means that if we place a small planar element of area delta S normal to E at a point, the number of field lines crossing to it is proportional to E delta S. Now suppose we tilt the area element by an angle theta. Clearly, the number of field lines crossing the area element will be smaller. The projection of the area element normal to E is delta S cos theta. Thus, the number of field lines crossing delta S is proportional to E delta S cos theta, where theta equals to 90 degree. Field lines will be parallel to delta S and will not cross it at all. The orientation of area element and not merely its magnitude is important in many concepts. For example, in a stream, the amount of water flowing through a ring will naturally depend on how you hold the ring. If you hold it normal to the flow, maximum water will flow through it than if you hold it some other orientation. This shows that an area element should be treated as a vector. It has a magnitude and also a direction. How to specify the direction of a planar area? Clearly, normal to the plane specifies the orientation of the plane. Thus, the direction of a planar area vector is along its normal. How to associate a vector to the area of the curved surface? We imagine dividing the surface into a large number of small area elements. Each small area element may be treated as a planar and a vector associated with it, as explained before. Notice one ambiguity is here. The direction of an area element is along its normal, but a normal can point in two directions. Which direction do we choose as direction of area vector associated with the area element? This problem is resolved by some conventional appropriate to the given context. For the case of closed surface, this convention is very simple. The vector associated with every area element of the closed surface is taken to be in the direction of outward normal. This is the convention used in figure 1.19. Thus, the area element vector delta S at a point on a closed surface equals to delta Sn, where delta S is the magnitude of the area element and n is the unit vector in the direction of outward normal at the flux. We now come to the definition of electric flux. Electric flux delta phi through an area element delta S is given by delta phi is equal to E delta S, which is equal to E delta S cos theta, which is as seen before, is proportional to the number of field lines cutting the area element. The angle theta here is the angle between E and delta S for the closed surface. With the convention stated already, theta is the angle between E and the outward normal to the area element. Notice we could look at the expression E delta S cos theta in two ways, that is E into delta S cos theta, that is E times the projection of area normal to E, or E perpendicular into delta S, that is component of E along the normal to this area element times the magnitude of area element. The unit of electric flux is Newton per coulomb meter square. The basic definition of electric flux is given by the equation can be used in the principle to calculate the total flux through any given surface. All we have to do is to divide the surface into small area elements, calculate the flux as each element and add them up. Thus, the total flux phi through a surface is phi is almost equal to summation of E dot delta S. The approximation sign is put because Electric field E is taken to be constant over a small area element. This is mathematically exact only when you take the limit as delta S to 0. The sum in the equation is written as an integral. 1.11 Electric dipole. An electric dipole is a pair of equal and opposite charges q and minus q separated by a distance 2a. The line joining the two charges defines a direction in space. By convention, the direction from minus q to q is said to be the direction of dipole. The midpoint of locations of minus q and q is called the center of the dipole. The total charge of the electric dipole is obviously 0. This does not mean that the electric field of the electric dipole is 0. Since the charge q and minus q are separated by some distance, the electric fields due to them when added do not exactly cancel out. However, at distance much larger than the separation of the two charges forming a dipole, the fields due to q and minus q nearly cancel out. The electric field due to the dipole therefore falls off. At a large distance, faster than like 1 upon r squared, the dependence of r on the field due to single charge q. These qualitative ideas are borne out by explicit calculations as follows. 1.11.1 Field of an electric dipole. The electric field of the pair of charges at any point in space can be found out from the Coulomb's law and the superposition principle. The results are simple for the following two cases. Number 1, when the point is on the dipole axis, and number 2, when it is at the equatorial plane of the dipole, that is, on the plane perpendicular to the dipole axis through its center. The electric field at any general point P is obtained by adding the electric fields E minus Q due to charge minus Q and E plus Q due to charge plus Q by the parallelogram law of vectors. Number 1, for points on the axis. Let point P be the distance r from the center of the dipole on the side of the charge Q as shown in the figure. Then E minus Q is equal to minus QP upon 4 pi epsilon naught r plus a whole square, where P is the unit vector on a dipole axis from minus Q to plus Q. Also, E plus Q is equal to QP upon 4 pi epsilon naught r minus a whole square. The total field at P is E is equal to E plus Q plus A minus Q. And for r greater than a, E is equal to 4QA upon 4 pi epsilon naught r cube P. For points on the equatorial plane, the magnitude of the electric field due to the two charges plus Q and minus Q are given by the following equations and are equal. The directions of E plus Q and E minus Q are shown in the figure. Clearly, the components of the normal to the dipole axis cancel away. The components along the dipole axis add up. So the total electric field is opposite to P. We have E is equal to minus 2QA upon 4 pi epsilon naught r squared plus a squared whole to the power 3 by 2p. At larger distances, that is r very greater than a, it reduces to E is equal to minus QA upon 4 pi epsilon naught r cube p. From the above equations, it is clear that the dipole field at large distances do not involve Q and A separately. It depends on the product of QA. This suggests that the definition of dipole moment, that is, the dipole moment vector P of an electric dipole, is given by P is equal to Q into 2A. That is, the vector whose magnitude is charge Q times the separation of 2A, and the direction is along the line from minus Q to plus Q. In terms of P, electric field of a dipole at large distances takes simple forms. At a point on the dipole axis, E is equal to 2p upon 4 pi epsilon naught r cube. At a point on the equatorial plane, E is equal to minus p upon 4 pi epsilon naught r cube. Notice the important point on the dipole field at large distances falls off as 1 upon r square but as 1 upon r cube. Further, the magnitude and the direction of the dipole field depends only upon the distance r but also on the angle between the position vector r and dipole moment p. We can think of limit when the dipole of size 2a approaches 0 and the charge q approaches infinity in such a way that the product of p equals to q into 2a is finite. Such a dipole is referred to as point dipole. For a point dipole, the equations are exact and true for any r. 1.11.2 Physical significance of dipoles. In most molecules, the center of positive charges and of negative charges lie at the same plane. Therefore, their dipole moment is 0. CO2 and CH4 are of these type of molecules. However, they develop a dipole moment when an electric field is applied. But in some molecules, the charges of the negative charges and of the positive charges do not coincide. Therefore, they have a permanent electric dipole moment even in the absence of an electric field. Such molecules are called polar molecules. Water molecules H2O is a type of this. Various materials give rise to interesting properties and important applications in the presence or absence of electric field. I'm skipping example 1.10 for you to solve it later, or you may pause the video and solve it right now. 1.2 Dipole in a uniform external field. Consider a permanent dipole of dipole moment P in a uniform external field E as shown in the figure. By permanent dipole, we mean that P exists irrespective of E. It is not being induced by E. This is a force QE on Q and a force minus QE on minus Q. The net force on the dipole is 0 since E is uniform. However, the charges are separated, so the forces act at different points, resulting in a torque on the dipole. When net force is 0, the torque is independent of the origin. This magnitude equals to the magnitude of each force multiplied by the arm of the couple, that is the perpendicular distance between two anti-parallel forces. The magnitude of torque is equal to QE into 2A sin theta, which is equal to 2QAE sin theta. This direction is normal to the plane of the paper coming out of it. The magnitude of P cross E, also PE sin theta, is its direction, is normal to the paper coming out of it. Thus, torque tau is equal to P cross E. This torque will tend to align the dipole with the field E. When P is aligned with E, the torque is 0. What happens if the field is not uniform? In that case, the net force will evidently be non-zero. In addition, there will in general be a torque on the system as before. The general case is involved so as to consider the simpler situations when P is parallel to E or anti-parallel to E. In either case, the net torque is 0, but there is a net force on the dipole if E is not uniform. The figure is self-explanatory. It is easily seen that P is parallel to E. The dipole has net force in the direction of increasing field when P is anti-parallel to E. The net force on the dipole is in the direction of decreasing field. In general, the force depends upon the orientation of P with respect to E. This brings us to a common observation in frictional electricity. A comb run through a dry air attracts pieces of comb paper. The comb, as we know, acquires charge through the friction, but the paper is not charged. What then explains the attractive force? Taking the clue from the preceding discussion, the charged comb polarizes the piece of paper, that is, induces net dipole moment in the direction of field. Further, the electric field due to comb is not uniform. This non-uniformity of the field makes dipole to experience a net force on it. In this situation, it is easily seen that the paper should move in the direction of comb. 1.13 Continuous charge distribution. We have so far dealt with charge configurations involving discrete charges Q1, Q2 and so on till Qn. One reason why we restrict it to discrete charges is that the mathematical treatment is simpler and does not involve calculus. For many purposes, however, it is impractical to work in terms of discrete charges and we need to work with continuous charge distributions. For example, on the surface of a charged conductor, it is impractical to specify the charge distribution in terms of locations of the microscopic charge constituents. It is more feasible to consider an area element delta S on the surface of the conductor, which is very small on the macroscopic scale but big enough to include very large number of electrons, and specify the charge del Q on that element. When we define a surface charge density sigma at the area element by sigma is equal to delta Q upon delta S. We can do this at different points of the conductor and arrive at a continuous function sigma, called the surface charge density. The surface charge density sigma also ignores the quantization of charge and is the continuity in charge distribution at microscopic level. Sigma represents macroscopic surface charge density, which is a sense it is smoothed out in the average of the microscopic charge density over an area element delta S, which, as said before, is large microscopically but small macroscopically. The units for sigma are coulomb per meter squared. Similar considerations apply on the line charge distribution and a volume charge distribution. The linear charge density lambda of a wire is given by lambda is equal to del Q upon del L, where del L is a small line element on the wire on the macroscopic scale that however includes large number of microscopic charged constituents, and delta Q is the charge contained in that line element. The units for lambda are coulomb per meter. The volume charge density, sometimes simply called charge density, is defined in the similar manner, where rho is equal to delta Q upon delta V, where delta Q is the charge included in the macroscopically small volume element delta V that includes large number of microscopic charged constituents. The unit for rho are coulomb per meter cube. The notion of continuous charge distribution is similar to that we adopt for continuous mass distribution in mechanics. When we refer to density of a liquid, we are referring to its macroscopic density. We regard it as a continuous fluid and ignore its discrete molecular constitution. The field due to the continuous charge distribution is obtained in much same way for a system of discrete charges. Suppose a continuous charge distribution in space has a charge density ρ. Choose any convenient origin O and let the position vector of any point in the charge distribution be r. The charge density ρ may vary from point to point, that is a function of r. Divide the charge distribution into small volume sizes of size delta V. The charge in a volume element delta V is ρ delta V. Now consider any general point P inside or outside the distribution with position vector r. Electric field due to the charge ρ delta V is given by Coulomb's law, where delta is equal to 1 upon 4 pi epsilon naught rho delta V upon r dash square, where r dash is the distance between the charge element P and r, is a unit vector in the direction from charge element to P. By the superposition principle, the total electric field due to the charge distribution is obtained by summing over the electric fields due to different volume elements. E is almost equal to 1 upon 4 pi epsilon naught summation of rho delta V upon r dash square. Note that rho, r dash and unit vector r all can vary from point to point. In a strict mathematical method, we would let delta V to 0 and the sum then becomes an integral, but we omit that discussion here for simplicity. In short, using Coulomb's law and superposition principle, electric field can be determined for any charge distribution, discrete or continuous, or a part of discrete and part continuous. 1.14 Gauss law. As a simple application in the notion of electric flux, let us consider the total flux here through a sphere of radius r, which includes a point charge q at its center. Divide the sphere into many small area elements as shown in the figure. The flux through an area element delta S is del phi is equal to E dot delta S, which is equal to q upon 4 pi epsilon naught r square unit vector r delta S, where we have used Coulomb's law for electric field due to a single charge q. The unit vector r is along the radius vector from center to the area element. Now, since the normal to the sphere at any point is along the radius vector at that point, the area element delta S and r have the same direction. Therefore, delta phi is equal to q upon 4 pi epsilon naught r square delta S. Since the magnitude of unit vector is 1, the total flux through the sphere is obtained by adding up the flux through the different area elements, where phi is equal to summation of q upon 4 pi epsilon naught r square delta S. Since each area element of the sphere is at the same distance r from the charge, phi is equal to q upon 4 pi epsilon naught r square summation of delta S. Now S, the total area of sphere, is equal to 4 pi r square. Thus, phi is equal to q upon 4 pi epsilon naught r square into 4 pi r square, which is equal to q upon epsilon naught. This equation is the simple illustration of a general result of electrostatics called the Gauss law. We state Gauss law without proof. Electric flux through a closed surface S is equal to q upon epsilon naught, where q is the total charge enclosed by S. The law implies that the total electric flux through a closed surface is 0 if no charge is enclosed by the surface. We can see that explicitly in the simple situation in the figure. Here the electric field is uniform and we are considering a closed cylindrical surface with its axis parallel to the uniform field E. The total flux phi through the surface is phi equals to phi 1 plus phi 2 plus phi 3, where phi 1 and phi 2 represents the flux through the surfaces of A1 and 2 of the circular cross section of the cylinder, and phi 3 is the flux through the curved cylindrical part of the closed surface. Now, normal to the surface 3 at every point is perpendicular to E. So by definition of flux, phi 3 is equal to 0. Further, the outward normal to 2 is along E, while the outward normal to 1 is opposite to E. Therefore, phi 1 is equal to minus ES1 and phi 2 is equal to plus ES2, where S1 is equal to S2 is equal to S, where S is the area of circular cross section. Thus, total flux is 0, as expected by Gauss law. Thus, whenever you find the net electric charge enclosed by a closed surface is 0, we conclude that the total charge contained in the closed surface is 0. The great significance of Gauss law by the equation 1.31 is that it is true in general and not only for simple cases we have considered above. Let us note some important points regarding this law. Number 1. Gauss law is true for any closed surface no matter what its shape is or size. Number 2. The term Q on the right hand side of the Gauss law includes the sum of all charges enclosed by the surface. The charges may be located anywhere inside the surface. Number 3. In the equation, when the surface is so chosen that there are some charges inside and some outside, the electric field whose flux appears on the left side of the equation is due to all the charges both inside and outside S. The term Q on the right hand side of the Gauss law, however, represents only the total charge inside S. Number 4. The surface that we choose for application of Gauss law is called the Gaussian surface. You may choose any Gaussian surface and apply Gauss law. However, take care not to let the Gaussian surface pass through any discrete charge. This is because electric field due to a system of discrete charges is not well defined at the location of any charge. As you go close to the charge, the field grows without any bound. However, the Gaussian surface can pass through the continuous charge distribution. Gauss law often useful towards much easier calculation of the electrostatic field where the system has some symmetry. This is facilitated by the choice of suitable Gaussian surface. Number 6. Finally, Gauss law is based on the inverse square dependence upon the distance contained in the Coulomb's law. Any violation of Gauss law will indicate departure from the inverse square law. I'm skipping example point 1.1 for you to solve it later, or you may pause the video and solve it right now. Same goes for example 1.12 as well. 1.15 Applications of Gauss law. The electric field due to the general charge distribution as seen above is given by the equation 1.27. In practice, except for some special cases, the summation or integration involved in this equation cannot be carried out to give specific electric field at every point in the space. For some symmetric charge configuration, however, it is possible to obtain the electric field in a simple way using Gauss law. This is best understood by some examples. 1.15.1 Field due to an infinitely long straight uniformly charged wire. Consider an infinitely long thin straight wire with uniform linear charge density lambda. The wire is obviously an axis of symmetry. Suppose we take the radial vector from O to P and rotate it around the wire. The points P, P dash and P double dash so obtained are completely equivalent with respect to the charged wire. This implies that the electric field must have the same magnitude at these points. The direction of the electric field at every point must be radial, that is outward if lambda is greater than 0 and inward if lambda is less than 0. This is clear from the figure. Consider a pair of line elements P1 and P2 of the wire as shown. The electric fields produced by the two elements of the pair when summed up give a resultant electric field which is radial. The components are normal to the radial vector cancelled. This is true for any pair of and hence total field at any point P is radial. Finally, since the wire is infinite, the electric field does not depend upon the position of P along the length of the wire. In short, the electric field is everywhere radial in the plane, cutting the wire normally, and its magnitude depends upon the radial distance r. To calculate the field, imagine an cylindrical Gaussian surface as shown in the figure. Since the field is everywhere radial, flux through the two ends of the cylindrical part of the surface, E is normal to the surface at every point, and its magnitude is constant. Since it depends only on r, the surface area of the curved part is 2 pi rl, where L is the length of the cylinder. Flux through the Gaussian surface is equal to flux through the curved cylindrical part of the surface, which is equal to E into 2 pi rl. The surface includes the charge equal to lambda L, where Gauss law then gives E into 2 pi rl is equal to lambda L upon epsilon naught. That is, E is equal to lambda upon 2 pi epsilon naught r. Vectorially, E at any point is given by E is equal to lambda upon 2 pi epsilon naught r n, where n is the radial unit vector of the plane normal to the wire passing through the point. E is directed outward if lambda is positive and inward if lambda is negative. Note that when we write a vector A as scalar multiplied by a unit vector, that is, A is equal to A unit vector A, the scalar A is an algebraic number. It can be positive or negative. The direction of A will be the same as the unit vector small a if A is greater than 0 and opposite to small a if A is less than 0. When we want to restrict to non-negative values, we use the symbol bar A. and call it the modulus of A. This modulus of A is greater than or equal to 0. Also note that only through a charge enclosed by a surface was included above. The electric field E due to the charge on the entire wire. Further, the assumption that the wire is infinitely long is crucial. Without this assumption, we cannot take E to be normal to the curved part of the cylindrical Gaussian surface. However, the equation is approximately true for electric field around the central portions of the long wire, where the end effects may be ignored. 1.15.2 Electric field due to uniformly charged infinite plane sheet. Let sigma be the uniform charge density of an infinite plane sheet. We take x-axis normal to the given plane. By symmetry, the electric field will not depend on y and z coordinates and its direction. At every point must be parallel to the x direction. We can take the Gaussian surface to be a rectangular parallelepiped of the cross-sectional area A as shown. The cylindrical surface will also do. As seen from the figure, only the two faces 1 and 2 will contribute to the flux. Electric field lines are parallel to the other faces and they therefore do not contribute to the total flux. The unit vector normal to the surface 1 is in minus x direction, while the unit vector normal to the surface 2 is in the plus s direction. Therefore, flux E dot delta S through both the surface are equal and add up. Therefore, the net flux through the Gaussian surface is 2EA. The charge enclosed by the closed surface is sigma A. Therefore, the Gauss law 2EA is equal to sigma A upon epsilon naught, or E is equal to sigma upon 2 epsilon naught. Pictorially, E is equal to sigma upon 2 epsilon naught n, where n is the unit vector normal to the plane and going away from it. E is directed away from the plate if sigma is positive and towards the plate if sigma is negative. Note that the above application of Gauss law has brought to an additional fact, that is, E is independent of x also. For infinitely large planar sheet, the equation is approximately true in middle regions of the planar sheet away from its ends. 1.15.3 Field due to uniformly charged thin spherical shell. Let sigma be the uniform charge density of a thin spherical shell of radius r. The situation was obvious spherical symmetry. The field at any point P outside or inside can depend only on r, that is the radial distance from the center of the shell to the point, and must be radial, that is along the radius vector. Number 1. Field outside the shell. To consider a point P outside the shell with radius vector r. To calculate E at P, we take the Gaussian surface to be the sphere of radius r and with the center O passing through P. All points on the sphere are equivalent relative to the given charged configuration, that is, we mean by spherical symmetry. The electric field at each point on the Gaussian surface therefore has same magnitude E and is along the radius vector at each point. Thus, E and delta S are every point are parallel to the flux through each element E delta S, summing all over delta S. The flux through the Gaussian surface is E into 4 pi r squared. The charge enclosed is sigma into 4 pi r squared. By Gauss law, E into 4 pi r square is equal to sigma upon epsilon naught 4 pi r square, or E is equal to sigma r square upon epsilon naught r square, which is also equal to Q upon 4 pi epsilon naught r square, where Q is equal to 4 pi r square sigma is the total charge on the spherical cell. Vectorially, E is equal to Q upon 4 pi epsilon naught r square r, where the electric field is directed outward if Q is greater than 0 and inward if Q is less than 0. This, however, is exactly the field produced by charge Q placed at the center O. Thus, for points outside the shell, field due to a uniformly charged shell is as if the entire charge of the shell is concentrated at its center. Number 2. Field inside the shell. In the figure 1.31b, the point P is inside the shell. The Gaussian surface is again a sphere through P centered at O. The flux through the Gaussian surface, calculated as before, is E into 4 pi r squared. However, in this case, the Gaussian surface encloses no charge. The Gauss law then gives E into 4 pi r squared is equal to 0. That is, E is equal to 0. That is, the field due to a uniformly charged thin shell is 0 at all the points inside the shell. This important result is the direct consequence of Gauss law, which follows the Coulomb's law. The experimental verification of this confirms the 1 upon r square dependence in Coulomb's law. I'm skipping example 1.13 for you to solve it later, or you may pause the video and solve it right now. go through the summary by yourself, and I'll be switching it over directly to the points to ponder. Points to ponder. Number 1. You might wonder why the protons, all carrying positive charges, are compactly residing inside the nucleus. Why do they not fly away? You will learn that there is a third kind of a fundamental force called the strong force which holds them together. The range of distance where this force is effective is, however, very small, that is 10 to the power minus 14 meter. This is precisely the size of the nucleus. Also, the electrons are not allowed to sit on the top of the protons, that is inside the nucleus, due to laws of quantum mechanics. This gives the atoms their structure as they exist in nature. Number 2. Coulomb's force and gravitational force follows some inverse square law, but gravitational force has only one sign, that is always attractive, while Coulomb force can be of both the signs, attractive and repulsive, allowing the possibility of cancellation of electric charges. This is how gravity, despite being much weaker force, can be a dominating and more pervasive force in nature. The constant of proportionality K in Coulomb's law is a matter of choice if the unit of charge is to be defined using Coulomb's law. In SI unit, however, what is defined as the unit of current A via its magnetic effect Ampere's law, and unit of charge Coulomb is simply defined as 1 Coulomb is equal to 1 ampere second. In this case, the value of K is no longer arbitrary. It is approximately 9 into 10 to the 9 Newton meter square per Coulomb square. Number 4. Rather large value of K, that is the large size of the unit of charge, from the point of view of electric effect arises because the unit of charge is defined in terms of magnetic forces, which are generally much weaker than the electric forces. Thus, while 1 ampere is the unit of reasonable size of magnetic effects, 1 Coulomb is equal to 1 ampere second is too big a unit for electric effects. Number 5. The additive properties of charge is not an obvious property. It is related to the fact that electric charge has no direction associated with it, as charge is a scalar. Number 6. Charge is not a scalar under rotation. It is also invariant for frames of reference in relative motion. It is not always true for every scalar. For example, kinetic energy is a scalar under rotation, but it is not invariant for frames of reference in relative motion. Number 7. Conservation of total charge of an isolated system in a property independent of scalar nature of charge, noted in point 6. Conservation refers to invariance in time in a given time frame of reference. A quantity may be scalar but not conserved, like kinetic energy in an elastic collision. On the other hand, one can be conserved vector quantity, for example, angular momentum in an isolated system. Number 8. Quantization of electric charge is a basic law of nature. Interestingly, there is no analogous law on quantization of mass. Number 9. Superposition principle cannot be regarded as obvious or equated with the law of addition of vectors. It has two things. Force on one charge due to another charge is unaffected by the presence of other charges, that is, there are no additional 3-body, 4-body, etc. Forces which arise only when there are more than 2 charges. Number 10. Electric field due to a discrete charge configuration is not defined at the locations of the discrete charges. For continuous volume charge distribution, it is defined as any point in the distribution. For a surface charge distribution, electric field is discontinuous across the surface. And number 11. The electric field due to charge configuration with total charge 0 is not 0. But for distances large compared to the size of the configuration, the field falls off faster than 1 upon r squared, typical of field due to single charge. An electric dipole is the simplest example of this fact. So that's the end of the chapter, but do not forget to solve each and every question of the exercises, especially the additional exercise, because as you may see, the 2020 paper of NEET was somehow directly from the NCERT textbook of physics as well, including physics and chemistry and biology. So do not forget to solve each and every question, including the examples, exercises, additional exercises and everything. So till then, subscribe to this channel and stay tuned. We'll see you again in the next one. Thank you.